Welcome back. In the previous lecture, we had talked about contour integration and introduced the notion of homotopy and simple connectedness. To recall, in that lecture, I had given an exercise relating the existence of primitive yeah. So when we talked about the path independence, I had given this exercise that for a continuous function on a domain omega, f admits a single valued primitive if and only if its integral over every loop in omega is 0. Okay, so this is something which I had given an exercise in the previous lecture. So this basically tells you that the integral over 0 is equivalent to saying that the function has a primitive. Now we will take this further and we will see in this lecture that for holomorphic functions f, this is always the case under some conditions on the domain. For simple connected domains, that means for holomorphic functions always admit a primitive and so on. So here we have seen in some examples as well. We say that, for instance, take the case the constant function 1 in the plane C. This has a primitive which is the function z, right? The identity function z is a primitive of the constant function 1 in C, and that constant function 1 is actually 0 for every loop in C. In fact, we had given this example of z power k in the previous exercise. Maybe it's here, this one. So you see here that's the case. Now take the case when k is minus 1. We have seen it's the 1 over z, and 1 over z has does not have a primitive, or its integral is not 0. See, integral of 1 over z for any curve around the origin is not 0. It's 2 pi I, it's not 0, and therefore and equivalently it does not have a primitive. There is a primitive for 1 over z which is log z, but in a neighborhood of the origin, that is not even a well-defined function. It's a multi-valued function. To make it actually a meaningful function log z, you have to take a branch along the starting from the branch cut 0. So which means that if you want to make it meaningful, then you have to ignore any line. So you don't have a neighborhood in which uh, you can actually have, but other outside that origin, if you take any curve which is a loop which does not contain the origin, you will notice that the integral will be 0, because in that case you can always choose a branch cut which does not intersect the curve, right? You can actually choose branch cut along any curve which starting from the origin. Okay, so this equivalent. So we will start today's lecture with a proof of, yeah, with a proof of that result. I given as an exercise. I'm also not going to give you the full proof. I'm just going to give a sketch of the proof to give you an idea, because this is important in going ahead and proving the property for holomorphic. Existence of primitive for holomorphic functions and so on. So this. So the fundamental theorem. So you can see this as a fundamental theorem of calculus for the complex version. So what this says is that suppose we have a function f which admits a primitive. That means there is a capital F such whose derivative is left, and gamma is a piecewise differentiable curve. Here because this is an assumption that we are having mostly throughout, right? For when you are looking at a complex derivative and holomorphic functions. we are going to have gamma as smooth as we require for a particular statement or a problem. So gamma is a piecewise differentiable curve. Then from the fundamental theorem of calculus itself we know, because the integral over integral of f over gamma by definition is some integral over ab of something, but this f is given to have a primitive, so this f is f prime, a capital F prime here. This by the definition of the contour integral is the real integral. So this is a real integral now, right? This is just the Riemann integral of this quantity. This is nothing but the derivative of f composed with gamma. So this is the integral of derivative. This means that this is nothing but the value of f composed with gamma at b minus f composed with gamma at a. Okay, so the integral of derivative. So that's where we have used the fundamental theorem of calculus of the real case. So whenever f has a primitive, you can actually compute this integral. Now the point about this is that whenever you have a loop, that is whenever the gamma is closed, then gamma b is gamma a, which means that these two values are same, so this is 0. So for a loop, integral of f over gamma is 0. So whenever f has a primitive, the integral of f over a loop is always 0. This is the one side situation. Conversely, you want to also say that whenever the integral is 0, then the f will have a primitive. So let's start with an f whose integral is 0 for all loop in gamma. Then we need to say that f has a primitive, which means we need to find a capital F whose derivative is little f. So we need to define that capital F. The way you define the capital F is that you fix a point z0, some arbitrary point you fix it z0, and you define fz to be the integral of the little f along a curve which joins z0 to this z. So you have fixed a z0, then you take then for every other point z you join a curve. Now this is, so there are more than one possibility of doing this, right? So there are many curves which will join from z0 to z, but that's fine. You take any path, any curve joining z0 to z. So the value of f at z is nothing but the integral of little f over that curve for any path, okay, joining z0 and z. But given that the fact that the given little function little f integral over loop is 0 ensures that this definition is independent of the path that you choose. Why? Because if you take one path from z0 to z, if you take another path from z0 to z, then you actually have a closed loop starting from z0 and coming back to, you have a loop, right, closed curve starting from z0 and coming back to z0. Now integral over that is 0 is what is given to you, because that's a loop, which means that whether you go via this path and go via that path, the other path, the integral is same, right? That is the path independence that we have seen. So now that you have checked the kind of validated that capital F is well defined, now you need to show that f prime, that capital F prime is little f. How do you show? Go by the usual notion of derivative. So you start with fz plus h, then minus fz. Okay. If you start with fz plus h minus fz, in terms of this integral, you will have z0 to z plus h minus z0 to z. If you subtract that, you are going to get the integral over the curve joining z to curve joining z to z plus h. of this little f, and there is a 1 over h here when you divide. Now, as limit of h goes to 0, you need to show that limit of 1 over h integral z to z plus h of f is the is little f, right? That's what you need to show. So again, so you can bring, so you need to show that's little f. So you bring minus f of z here, and you need to show limit of that is equal to 0. So limit of h going to 0, 1 over h z to z plus h f minus fz is equal to 0. Now this fz, so in front of this fz, with the fz you actually multiply and divide by h. Okay, so you can actually since as we said this is a curve joining z to z plus h, you can always choose any curve. So without loss of so you just choose the straight line from z to z plus h. Okay, so you start with that straight line, use that, and in front of f of z here you multiply and divide by h, and that h you write as an integral of integral of the constant function from z to z plus h. Okay, and if you pass to the limit there, you will see that you will get 0. So this part I leave you to complete. Okay, you just have to check that this derivative of capital F is little f. Okay, so now with this we can get into the um, some equivalent properties of holomorphic function. Okay, so I'm leaving this as an exercise to this. So I just want to highlight here that this is so generalization of this statement that whenever integral is 0, then the function has a primitive or something. This is the statement that this statement you generalize to holomorphic function, and that is a case of Morera's theorem, which tells you that whenever the function, integral is 0, Morera's theorem tells you that that function has a so it's holomorphic. Okay. Anyway, so and we are not going to do more, which is why I've said we are not going to prove Morera's theorem in this lecture and so on. So I just wanted to relate it. You must have seen this before. One of you even talked about it in your presentation. Okay. So what is Cauchy's theorem? Cauchy's theorem tells you that if you that for any holomorphic function f, it's holomorphic in omega. For any holomorphic function f, its integral over counterclockwise simple loop in a simply connected set omega is 0. So if f is holomorphic on a simply connected open set omega, then integral over every loop is 0. And this is equivalent to saying from the previous statement that every holomorphic function on a simply connected domain has a primitive. Okay, so we will prove this theorem with some. We'll prove this theorem in 2 steps. So one, let's start with integral of f over the loop. Now f has a real and imaginary part u plus iv, right? u plus iv. Z has the real and imaginary part x, y. So this is d and dx plus I dy. So you do this computation, separate the real and imaginary part of the integrand here. You are going to get this. Okay. So this is a line integral of some function u x comma y, because this is a 2 variable function but integral over 1 variable. This is also a 2 variable function but integrated over 1 variable, the line integral, similar function here. And this is nothing but the result of Green's theorem. So Green's theorem tells you that this line integral is equal to this double integral. So you apply Green's theorem for this, you get this. You apply Green's theorem for this, you get this. Green's theorem is a statement in two dimensions. This is like the Stokes theorem in three. So this is the Stokes theorem version in 2 dimension. You can think of it like that. I am going to give you a proof of this in the next slide. I'm just going to take up from here. So if you assume Green's theorem, then you have this line. You can write this line integral, path integral, in terms of this double integral. And what are the one that is inside? Now here, because f is holomorphic, you can use the Cauchy Riemann equations. And you can actually see that these are 0. These integrands are 0 here. Because by Cauchy Riemann equation, ux is vy, this is 0. Minus vx is uy, so this is also 0. So you actually have this entire integral is 0. So you actually have integral of f is 0. So what did we use to prove this result? We just used Green's theorem and the Cauchy Riemann equation. So Cauchy Riemann equation is something we have already established in one of the previous lecture. So if we prove Green's theorem, then our proof is complete here in this respect. So this tells you that for a holomorphic function, the integral over loop is always 0 for a simply connected domain. Okay, so so let's go and prove the Green's theorem. Okay. So let gamma be a counterclockwise loop, simple loop in C, and U is the so we have already seen that for a simple loop it separates the plane into two disconnected components, and there is a bounded component and unbounded component. So this U is denoting the bounded component enclosed by the curve. Okay, so use that part. So you can think of that as an interior part, right? So P and Q are functions or two variable functions or functions on C or from R2 to R, right? P and Q are functions which admit continuous partial derivatives, right, in U closure gamma. Okay. What I mean is that you have partial derivatives here, and the partial derivatives are continuous, and they can also be continuously extended to the loop gamma. That's what I mean here. So then the integral of p dx qy over the curve over the loop is nothing but the double integral. This is precisely what we used in the previous theorem. So what is the proof of this? So the proof is, for this we need to understand this bounded region U. So we just, for simplicity, I take a curve like this. This circle, so the circle is our loop gamma, let's say. So this and U is the region bounded by gamma. I mean, and the region enclosed by gamma. So the interior of gamma. So this interior of gamma is U, right? Now this U can be interpreted in both ways. This is something like you do if you have come across Fubini's theorem, changing the order of integration. So this U can be interpreted in two ways. That is, I can think of this as the union over all the vertical lines for each horizontal point, right? Or I can think of this same set as all horizontal lines, union of all horizontal lines for each point on a vertical line, right? So how you do this double integration, whether you sum over x first and then you sum over y, or you sum over y first and then sum over x. This is the order of integration, Fubini's theorem. So we will use that fact here. So that's why I've given this same U in two different forms. So the first case, when we deal with the case P, because there's a Py, we first want to integrate it over the x, over the y variable and then over the x variable. In this case, we will first integrate with respect to the x variable and then over the y variable on u. So we are going to interpret u in a different way for each of this function, and that is not going to change anything, right? So the way I'm going to view this gamma is, now this gamma is as union of gamma 1 and gamma 2. Actually, if you include the orientation, it's counterclockwise. So I'm going to view gamma as union of gamma 1 and union and minus gamma 2. Okay, now gamma 1 union minus gamma 2 is the curve gamma. The way we are going to see it is that, so you see this point where this red and blue intersect. This is my point A, let's say, okay, and this is my point B. So you have this line start and joining from A to B, and you can think of these curves as map from the interval AB, which gives you these points. So gamma 1 is a map from AB, which gives you this blue line, and gamma 2 is the parameterization of that part of the curve from AB, which gives this, but the orientation is, so it's from AB, right? So orientation is like this. So you can think of u as union of x AB, where the singleton x, so for each fixed x in the interval AB, you have this vertical line, which is gamma 1x, which is the interval gamma 1x to gamma 2x, right? So for each x you have that. You do this over all x. Union of that is your u. A similar interpretation is we are doing here. What we are doing here is like this here. So you have A here, okay. You have A here, you have B here. This, so the AB is along this vertical line here, and these are the parameterization along the interval AB. Okay. In fact, the way I have given the orientation, I think A is at the top here and B is here. No, in that case, no. Actually, there is. I should have given the. I want to take A here. I want to take B here. That is what will work with QX. We are going to see it in the proof here. So you take A at the bottom, B at the B at the top here. So for each point on this vertical line, you have this horizontal line, which is from gamma 2. So if you call this point y, y is the point coming from this. So gamma 2y to gamma 1 to gamma 1x. That is how we are going to. So union of all these horizontal lines for each point on this vertical line. So this is another way of interpreting u. So let's take the one by one and see what happens with this. So let's take this notion of u and look at what happens to py. So integral of u minus py dx dy. So we are going to use the first interpretation of u. So it's now a map from A to B, gamma 1x to gamma 2x, right? That is how we have seen here. For EAB, gamma 1x to gamma 2x is the straight line. So you have, so this is now integral over, this is the y variable. So y variable is n. So we are basically using the fact that you can change the order of integration, because the domain respects that. So AB, now if you use your fundamental theorem of calculus with respect to the y variable, this is nothing but the evaluation of P at the end points, which is gamma 2 minus gamma 1, but with this minus you have this notion of, this sign. So gamma 1 minus gamma 2, P evaluated at those values. Now this first integral over A, P of x gamma 1 dx is nothing but the integral over the path gamma 1, right? Because y is now running over gamma 1. So this is actually integral of AB of this is nothing but the integral over the path gamma 1 in R2. Similarly, this is the integral of P over the path minus gamma 2. So this is nothing but integral over gamma 1 union minus gamma 2, which is integral over gamma. So you started with this. So you started with a quantity on the left hand side in the Green's theorem, and you have obtained one term from the you started one from the right hand side and you obtained one term in the left hand side. You do the same process for Q. So when you start with Qx, it's dx dy. So you use a u variable for the x variable here. So x is coming from AB. Y is coming from AB now. I had shown you here the vertical line here. Okay, and then x is coming from AB, and this is y is coming from AB, and x is from gamma 2 to gamma 1. So if you do an integration here with respect to the x variable, you are going to get this, and then again this is nothing but the path integral here like this, which is nothing but the integral over q here. Okay, so so you had A here, you had B here, and gamma 2, gamma 1 was this straight line. So what I was checking was if you had A and B here, you should have this orientation, which means that yeah, I think there is no problem. Yeah, okay. So this is you started with a right hand side term and you got a left hand side term. That's a proof of Green's theorem, and this completes the proof of Cauchy theorem, right? And in this case, though it's not very explicit, we have used the fact that it's simply connected because we have looked into the bounded region. That simple loop gave you one bounded region in the interior, and we have integrated over that bounded region here. Now, what is the generalized Cauchy theorem? Now, this is whatever statement that we made before can be generalized by removing the hypothesis that omega is simple connected. So, if now the omega is just an open connected set, okay, omega is an open connected set, and f is a holomorphic function on an open connected set, then you actually have a much more general statement than a Cauchy theorem, which is generalized Cauchy theorem. You can think of that like that. So it's that the integral of the function over two curves which are homotopic are same. So if gamma 1, gamma 2 are homotopic curves oriented counterclockwise, then integral of gamma 1 and integral over gamma 2 are same. Now this in fact, if you notice from the definition that we gave in the previous lecture, that for the homotopic curve, you can actually verify that homotopy is an equivalence relation. So you can identify two curves, we can say they are equivalent if they are homotopic to each other. So in fact, if you know this theorem, the previous Cauchy theorem that we proved is a consequence of this theorem, because in a simple connected domain omega, every loop is homotopic to a point. So the integral over a loop is integral over the point. A point you can think of is as a curve which takes the same value for all t, that is the constant curve. So which means that you are going to get that to be 0, right? Because you are going to, if you write over that curve, it is gamma prime t, something that will appear here, which is going to be 0. So uh, the speed of that curve is 0, right? So you are going to, so the integral over over a point is 0. So the previous theorem, previous statement of Cauchy theorem for simple connectedness actually follows from here. But we are not, we have done that separately because that is easier to prove for simple connected domain. And to prove this theorem, at least you need to show whatever we showed for simple connectedness for a disk. That's what requires for this theorem. So we will take that sequence. We have proved that theorem for a simple connectedness, and we will try to show that this you can drop the simple connectedness and show it for homotopic curves. So this is basically means a contour integral is invariant for homotopic curves. So here when I say homotopic curves, you can the way we had, at least the picture is even that I showed you for homotopic curves, is where both gamma 1 gamma 2 at the same start and end points. But you can also, but that's not necessary, you can also define homotopic curves when the curves don't have the same start and end point. um, you can extend this notion. In fact, the notions are equivalent if your curves are closed curves. Okay, so for closed curves, the homotopy definition does not necessarily need the same start and end points. So when we say here two curves are homotopic, we also mean that we don't necessarily mean that gamma 1 and gamma 2 as the same start and end point. That is also included, but you can also have gamma 1 like something like kind of concentric circles, right? It's a loop. So you need a closed curve. That's it. Once you have a closed curve, you can have it. So if you have two closed curves, you can talk of homotopy between them and all. Okay. So I'm going to give on a sketch of the proof here. So just some idea of how this works. So the simple connectedness definition is dropped. So you imagine this. So suppose I can put uh, both these curves in a simple connected domain. If I can find one simple connected domain and put both these curves such that it contains both gamma 1 and gamma 2 inside, then I can one can use the previous result actually to conclude this result, right? You can you take if they have the same endpoint, you just complete a closed contour using gamma 1 union minus gamma 2 and so on. That integral will be 0, and then you can obtain this result if you can put them in. But that may not always be the case. You may not be able to put these both these curves. You may not be able to find a simple connected domain containing both these curves always. If that is the case, then it's done. Proof is done. So we are going to give a piecewise, and we are going to prove this in a piecewise way, right? So what we do is the following. So once you have these two curves, gamma 1, gamma 2, and since it is given that gamma 1 and gamma 2 are homotopic, that means there is a kind of homotopy, right? There is a continuous map T from the square which maps, which kind of incrementally maps gamma 1, can actually deform gamma 1 to gamma 2, right? So this T is that map. So you have the image of that T, right? Image of that. So T, the domain of T is square. The image of T is the region that that is mapped. That is the region that gets mapped between gamma 1 and gamma 2, the continuous deformation region, right? That is the image of T. So what, and this all these are, so gamma 1 gamma 2 is gamma 1 gamma 2 is contained in omega, so they are homotopic in omega. So this image of T is contained in omega. So you look at the distance between, and I also want to say that sorry, I also want to anyway. So image of T is this, but notice that you are starting from a square. That square is a compact set in R2. T is a continuous map from that compact set, which means image of T is also, it's a compact. It's a continuous image of a compact set. So this is also compact. So you take the distance between this image of T and the boundary of omega. Okay, and you choose an epsilon such that 3 epsilon is less than that. Now, when can you do that? You can always do that. Is something that you can verify for yourself as an exercise, because this is a compact set, and image of T is a compact set, and del omega the boundary of omega. Okay, so they are not. Uh, there is some you can always, basically you can put a ball between these two, that I mean of radius less than 3 epsilon or something. That's what this means, right? And you can always do that because of the fact that omega is an open set and this is a compact set inside the open set. Okay, so that is something you need to verify. Okay, but easy to verify. Just take some if I mean assume that if you can't do this, you will get a contradiction. Okay, so um, then what you do, you choose disk. Now that you have chosen an epsilon, such that 3 epsilon is less than the distance from this. Now for every point in the image of T, you choose a disk of radius 2 epsilon. Now you see this is not going to intersect the boundary. That is why we chose an epsilon like that. This is not going to go and touch the boundary of omega. This will be completely in the interior. So choose disks of radius 2 epsilon. So if you do this for every z of image of T, you have lots of, so for each z you have a ball centered at z with 2 epsilon. So you have a cover, you have an, so choose the open disk. Okay, so you have an open cover for image of T. Okay, and because image of T is compact, by you can actually extract a finite subcover. So you actually have a finite collection of 2 epsilon radius disk which covers image of T. Now this gamma 1 gamma 2 is actually in the image of T. So this gamma 1 and gamma 2 both are in this are sitting inside this finite cover. And all these disks that you have chosen are actually simple connected domain. It's just that these gamma 1 and gamma 2 contain in the union of this simple connected domain. Okay, so this is whatever I already said, that because it's a continuous map and the domain is a square which is a compact set, its image is compact, and also because of that T is a continuous function on a compact set, T is also uniformly continuous. So because T is uniformly continuous for this given epsilon, whatever epsilon that you chose earlier, for that epsilon, you can actually find a delta, right? You can actually find a delta such that this happens. So here this choice is independent of T. So this delta is independent of T. In fact, it's uniformly continuous. It's independent of both T and S, right? So you can, so the choice of this delta does not depend on S and T. That's what. So for every epsilon, you can choose a delta without uniformly, and the same delta will work for all S and T here. So you have this uh, you have this um, inequality here, right, from the uniform continuity of T. So what we do here is that now I'm not I don't have a very good picture here, but what we are trying to say here is that you have this disk, finite number of disks which are covering is gamma 1 and gamma 2. So what you do, all these disks will intersect, right? So this disks will intersect. So you choose points on say gamma S1, okay, and on gamma S2, points on gamma S1 and gamma S2 which are in the intersection of two disks. This you do for every adjacent intersection. Okay, so you choose one point from gamma S1, one point from gamma S2. Now so these are two different curves. You see gamma S1, so for each S1, gamma S1 is one deformation in between. So let me show you So choose one point each from the intersection of adjacent disk on gamma s1 and gamma s2. Okay, and then you join that by line. So what I'm showing here, I'm giving you a different picture here. Hope this helps you explain. So this is the given curve gamma 1. This is the given on a given curve gamma 2. I have shown it as an annular kind of concentric circles. So gamma 1, and we need to show that integral over gamma 1 is same as the integral over gamma 2. And this homotopy, the image of T is this entire annular region, right? Because so the deformation from gamma 1 gamma 2, you can think of it as coming from gamma. It starts from gamma 1 and continuously deforms to go to gamma 2. So this colored region is the region where, so for choice of S1, S2 such that S1 minus S2 is less than delta, you have this colored region. This is precisely the region where, which is within the epsilon distance, or something that we said. So when within epsilon distance, and this entire region is covered by disks of radius 2 epsilon, right? So this region, which is within an epsilon distance, is sitting inside those disks, right? And these disks are intersecting. So let's say there is a disk here, and there is a disk here. So this point here and this point on gamma s1 and this point on gamma s2 is chosen such that both these points are in the intersection of two adjacent disks. Similarly, you do this for the next adjacent intersection. Keep on doing this. So you will get lines like, I have only shown you two here, but you can get one more line here, one more line here, one more line here. So these are the points that you have chosen in the intersection. What you will see is that you will see that this point, this point, this point, this point will lie in one disk of epsilon, because this was chosen in the intersection of adjacent disks. That means this is lying in this disk as well and this disk as well. This is lying in this disk as well and this disk as well. I mean, there's a disk I'm imagining here. I have not shown it in the picture. Okay. So this both these straight lines, or this region which is enclosed by this line here, bounded by this straight line and this straight line, is actually lying in one disk. And this you can do for every disk. So what you have done is this: you have separated, you have written down this colored region. You can uh, you can actually not, I should not say color region, I am saying this two contour, right? That is gamma s1 and gamma s2. Now you can write, so integral over gamma s1 and integral and minus integral over gamma s2 can be written as sum of integral over this closed contour, this loop. You see this loop, you start from this point, come down, go in this direction here up to this point, go up, go in this direction here. So you have a loop here already. Similarly, if you have another line here, you will have a loop here. So if you take integral of f over this closed loop, right, and if you do this for every such loop, the sum of that is nothing but, because if you, so let's take the next loop here. Again, you will start from here, go down, come here, go up, come here, and finish here. So what you have done here, if you notice that in the previous curve when we went up here, now in this curve we are going down here in the opposite direction. So when you sum them, they will cancel out each other. So this integral over this line will cancel out everywhere. Okay, and what you will get is the integral over gamma s1 minus integral over gamma s2, because for gamma s2 we always came in the opposite direction. So it will be minus gamma s2. So the union, so the sum of all these closed loops will give you the integral over this and this. So integral of gamma s1 minus integral of gamma s2 is sum of all these loops. but these are loops each contained in a simply connected disk of radius epsilon. So the integral of f over this closed loop is 0, and that is true for each disk, and we have only finite number of disks, so it's a finite sum. So this integral will be uh, 0. So what we have shown is that integral of gamma s1 is actually equal to integral of f over gamma s1 is equal to integral of f over gamma s2. This you have done shown. So you have actually shown that integral of f over gamma s1 is same as integral of f over gamma s2 whenever the curves are in the delta, whenever the s1s are in the delta distance, right? But starting from gamma 1, whatever argument we gave for gamma s1, gamma s2, starting from gamma 1, you can actually divide the interval of the s parameter of of finite number of delta lengths, right? So once you do a finite number of delta lengths, you only have finite number of steps to go from gamma 1 to gamma 2. So from gamma 1 you go to gamma s1, which is some epsilon. So gamma 1 you can think of as s0 or something, right? Some starting point whenever s is equal to 0. So this is the gamma s is equal to 0. From s is equal to 0 to whenever s is equal to delta, and then s is equal to 2 delta, when s is equal to 3 delta, and so on, you will finally reach this. So you just divide the domain of the s variable into delta parts, and for each delta you can give the same argument, and you have shown that gamma 0 is same as uh, gamma corresponding to s equal to 0 is same as integral over that is same as integral over gamma corresponding s equal to delta. So that argument gives you the complete proof. Okay, that's what I have said here. So for delta s1 minus s2, whenever it's less than delta, we have shown this, and you can do this incrementally for in a finite number of steps. You can start from gamma 1 to gamma 2 with curves which are satisfying this condition. So that's the proof of the invariance of contour integral for homotopic curves. Okay, so complete the details of this proof and so on here. Okay, okay, okay. So now there's another statement where when gamma is a loop simply. So here again we are kind of relaxing another condition. So omega is now an also a so simply connected open set, and gamma is a loop counterclockwise oriented in omega, and f is a holomorphic function on omega. But now it's holomorphic except at a point z0. Earlier we had holomorphic in the entire domain. Now we are saying it's holomorphic except at a point z0, but at that point z0 it's not holomorphic, but the function is continuous. So it's continuous everywhere including the point z0, but it fails to be holomorphic at z0. In that case as well you can conclude. So this is a weaker condition. So it's like the Cauchy theorem that we proved, but it's with a weaker statement. You don't have holomorphicity at the point z0, but what you have to compensate is continuity at z0, and that is enough to show that integral f is 0. In fact, if you club this statement with Moreira's theorem, which I stated some time back, then you actually have holomorphicity at z0. So what is this statement? So if you have a function which is holomorphic everywhere except at z0, that is, you don't know whether it's holomorphic at z0 or not, but if you know it's continuous everywhere including z0, then the function actually has to be holomorphic at z0 as well, and that is what makes this. So that's the, if you because by Moreira's theorem, if integral is 0, the function has to be holomorphic, so it has to be holomorphic at z0. So though I say it's a weaker theorem, though it's not visible as, that's the beauty of this holomorphic functions. So this is the statement. So let's prove this. So what you see here is actually the fact that f is continuous at z0 is actually ensuring that it's not holomorphic at z0, but it is not undefined or infinity there. Okay, though it fails to be holomorphic at Z0, it's a nice point in the sense that in a neighborhood of Z0, the function is bounded because continuity ensures that. Right? If you take any neighborhood of Z0, in that region, the function is bounded. So which means that at Z0 there is the function is not taking infinity, or it's not that it's not defined there, or right. So this continuity ensures that. So it actually behaves well at Z0, which is why we can expect this behavior. So what you do is that you at Z0, the point where you don't have holomorphicity, you take a circle of radius epsilon. Okay, choose some radius epsilon as small as you want, and then you take the ball or take the circle of radius epsilon centered at Z0. So f is continuous in the disk of radius epsilon centered at Z0, right? Because that is what is given to you. So it's a, and f is bounded in that disk, because if you take the closure of that as including the circle, it's a compact set. So it's a continuous function on that compact set. So it is going to be bounded in that region. Okay, and this gamma 2, that disk, that circle of radius epsilon, is homotopic to the given gamma. Okay, so we are in a simply connected domain omega, right? And you actually have this, that gamma 2 is homotopic to gamma. So the integral over gamma is same as integral over gamma 2. So it's enough to compute the integral of f over gamma 2. It's enough to show that integral of f over gamma 2 is 0 by the previous theorem, which is homotopic. But it's because f is bound. So let's start with mod of gamma 2 f dz. Because f is bounded, you can take the bound of f in the disk of radius epsilon outside. So when I say norm f infinity here is the supremum of f in this ball. Okay. So you take that, so supremum of this will come out. So this, what you will have is integral of gamma 2 of mod dz, which is nothing but the length of the curve. The length of the curve is 2 pi epsilon because the radius is epsilon. Now this is true for every epsilon, every choice of epsilon. Epsilon is arbitrary. So this means that this quantity can be made as small as you want, right? Which means that this quantity is 0. So we have our result that integral of gamma 2 is 0, which means integral of gamma is 0 because they are homotopic. So verify the statements that all these statements that I have told here. So we are also using topology. So throughout we have been using topology also, right? So that kind of also refreshes your topology content, right? Continuous image of compact sets, continuous function on compact sets, bounded, and all these kind of results we are using. Um, so check that. So verify this point where I said, which is very easy to see. Verify this, that gamma to homotopic to this, and so on. Verify that this quantity is independent of epsilon. You can actually choose this bound independent of epsilon. Right? It doesn't depend on the ball that your disk that you choose, and so on. So that completes. So you actually have a weaker statement as well. From here we will go to what is called the Cauchy integral formula. So what does Cauchy integral formula say? It says that for a simply connected domain omega, if f is holomorphic on a simply connected domain omega, and if gamma is a counterclockwise loop, simple loop in omega. Simple loop, as I said, is we have been using simple loop. It is a loop. It is a closed curve which is not self-intersecting, right? Omega. Then this statement is true. That is integral of 1 over 2 pi f of w over w minus s. So this integral is over w. W is coming from the curve loop. Z is any point in the domain. Okay, Z is any point in the domain. So when you look at this quantity, for z in any point in the domain, you have the following different values. Whenever the z is in the interior of the curve gamma, which we had always called u, whenever z is in u, then the value of this integral is the value of f at z. Okay, and whenever z is in the complement of u closure, that is it's outside the curve on the other component, then this integral is 0. And whenever z is on the gamma, so you see whenever z is on the gamma, one of the w can take the value z, so you have a blow up here. This is undefined case. Okay, so the good thing about nice thing about this proof is this fact that you see that just knowing the value of, if you know the f um, value of f on a curve gamma, then using this quantity you can compute the value of f in all the points inside gamma. So all the points inside gamma, the value of f at all the points inside gamma can actually be computed from just knowing the value of f at all the points on gamma. This is something we had already connected holomorphic functions to harmonic functions, and I had made a statement there about mean value property of harmonic functions and so on. This is kind of it's a property similar to that, right? The value of, so the knowledge of f on the curve gives you all the values of f in the interior of the curve. And this is actually a result from the Cauchy theorem, right? Because once you take a z which is outside the gamma, exterior to gamma, then you see w minus z is actually doesn't have any undefinedness in that region, right? So this function f w over w minus z for any z in omega minus u closure, this function is actually a holomorphic function in this region, omega minus u closure. Okay, and this is a loop in that region. This is a loop in that region, right? So basically, z is taken in the exterior, right? So z is in the exterior. So just take a ball around the z and look at the complement of that ball around z, and that domain. So in that domain, this is a holomorphic function. Okay, and the given curve and the given curve is not around the ball, right? It's completely sitting in that complement. So this is by the Cauchy theorem. This holomorphic function integral over the loop should be 0. So this is a consequence of the Cauchy theorem. So we only need to prove the first statement here. So what do? You start with this result, you add and subtract fz. Okay, you add and subtract. So minus fz plus fz. So the minus fz is absorbed here with g. So g is defined as fw minus fz over w minus z, where whenever w is not equal to z, and w is not equal to z in this case. Well, z is in the interior, w is on the curve, so w is not equal to z. So this is g, and the plus fz is this part where that integral is over w, so wz comes out. So what you have is just this. So this g, the way you defined is it's for w not equal to z, we have defined it like this. So at w equal to z, you define it as the derivative of f. That is basically limit of this function as w goes to z, right? So from this definition itself, you notice that g is actually continuous at z as well. So g is not holomorphic when w is equal to z, but g is continuous at z. So this satisfies the previous weaker hypothesis statement that you made. G is a holomorphic function except at z, but is continuous everywhere. So for this function, integral of g is 0 on every loop. So in particular on this loop as well. So this first statement is, so this integral is 0. Okay, now what remains is this. Here this is the integral over the curve gamma. right? Now what you do that you choose the unit disk centered at Z. Now that unit disk and this gamma are homotopic to each other. So the integral over this gamma is same as integral over that unit disk, right? So this quantity then we have already integrate and we have found the quantity which is actually 2 pi I, and that is how this constant comes. So 2 pi I comes here, so that if you divide you come here, so you get fz's, and that's precisely what you do here. So gamma is homotopic to the unit circle centered at Z, so you have the whatever we define. So this is the proof of Cauchy integral theorem. And there's a converse to the Cauchy integral theorem, which tells you that if f satisfies this condition for all z in the interior of gamma, okay, and f is defined on gamma as a continuous function, gamma is a simple loop counterclockwise oriented, and f satisfies this condition, then f is infinitely complex differentiable. In fact, it's all, and hence holomorphic. And the derivatives are given by this formula. Okay, this is the proof of, this is the statement of the converse of this the Cauchy integral formula. So this uh, actually tells you that if a function satisfies this formula, this condition, then the function is infinitely differentiable. So if you go back to the previous theorem, any holomorphic function, because it satisfies this condition, it is infinitely differentiable. So any holomorphic function is infinitely differentiable. That's a consequence of this statement. And the proof is actually very easy. So you know that f satisfies this condition. Um, f satisfies this condition. So what you do is that you take the derivative of f for every point z here. Okay, so you take the derivative of f in the z. When we say derivative of z, what we basically mean is usual thing, right? Z plus h minus f of z and so on. So if you take the derivative of z here, you see in this integral is over w. So the derivative of z is this is only over this. So if you take any kth derivative, the derivative is actually over 1 over w minus z. And this is something which you know is differentiable, and is precisely this quantity that you have here. So you can prove it like that. So that way we have shown that every holomorphic function is integrable. So in this lecture, what we have shown is that if you have a holomorphic function, it has primitive for simply connected domains. It also is infinitely differentiable, and knowing the function on on a curve is enough to compute the function in the in the region bounded or enclosed by the curve. Right? These are properties of holomorphic functions. So we'll stop here, and we will continue in the next lecture. Thanks.